Hello everyone. So today we are going to the next session of this chapter. Here we are discussing example 9.1, and that is non-interacting particles. So here the situation is two non-interacting particles of masses m1 and m2 move toward each other with velocities v1 and v2. Look at this picture. This is our masses particles of mass m1 and m2. They are moving towards each other. This mass is moving in this direction and this particle is moving in this direction, and the first particle is moving with the velocity v1 and the second particle is moving with the velocity v2. Their paths are offset by a distance p. So when they are meet together, or they reach in the same position, their distance between them is taken as b, and the distance between m1 and m2 is taken as r. R is varying. We know that r is varying when m1 and m2 are in motion. So here we will investigate the equivalent one body description of the system. This is a two body problem, and in the last classes we have studied that we can describe this type of problems into a one body problem. So we are searching the energy of this system using one body problem. So the relative velocity is, so the relative velocity of these two particles is taken as v0, and v0 is equal to r dot. This is the distance between m1 and m2. Therefore the dot product, r dot is the velocity. And what is r dot? R dot is r1 dot minus r2 dot, where r1 is the position vector of m1 and r2 is the position vector of m2, which is dr1 by dt. R1 is the position vector of m1 and r2 is the position vector of m2. These are we know these quantities r1 and r2 we have studied earlier. And what is r1 dot? R1 dot is v1, and what is r2 dot? It is v2. So v0 is v1 minus v2. And the energy of the system related to the center of mass. And we have studied what is the expression for the energy of the center of mass. And we know that this the sum of the kinetic energy and the potential energy, and which is equal to half mu v0 square plus u of r. And what is mu? Mu is the reduced mass of m1 and m2. Here we are considering the one body problem, and v0 is the relative velocity of the particles, and u of r is the potential energy. And in the heading itself it is saying that it is non-interacting particles. So for non-interacting particles the potential energy is equal to 0. Therefore the total energy is equal to half mu. This is not m, this is mu. It's a reduced mass, mu v0 square. Put equation number 1. And in order to find the energy diagram, we need U effective. We have to find U effective potential. And one thing I have to tell is that V1 and V2, V0 is constant. Because V1 is a constant and V2 is also a constant. Therefore the difference between them is a constant. Therefore V0 is constant velocity. Relative velocity is constant. So coming to this point, in order to find the energy diagram, now we have to plot an energy diagram for the system. We need U effective potential, and we know that the expression for effective potential is L square by 2 mu R square plus U of R. And as we said earlier, U of R for non-interacting particles are 0. Therefore, U effective potential is equal to L square by 2 mu R square. Put it equation number 2. And look at this picture. When the particle is moving towards each other, the particle is moving in this direction and M1 is moving in this direction. At one point they meet together, and at that point, this is the picture for that. And at that point the distance between M1 and M2 is B, and where R is a constant, and all the other times R is varying, and at this point R is equal to B and it is a constant. R is equal to B is a constant. At that time R dot is equal to 0. R dot is 0. So R dot is equal to 0. And U effective is equal to L square by 2 mu R square. Put B in the instead of R, therefore L square by 2 mu B square. We will get L square by 2 mu R square is equal to L square by 2 mu B square. So energy of the system is half m R dot square. Energy of the system is yes again mu, so it is half mu R dot square plus U effective, and we know that R dot square, R dot is equal to 0 at this particular position, and E is equal to L square by 2 mu B square. Okay, it is not M, it is mu. So at this the energy of this system is half mu R dot square plus U effective, and at this case R dot is equal to 0 and energy is equal to L square by 2 mu B square. This is the expression for U effective. Now the energy is L square by 2 mu B square, and in the equation number 1 we have seen that energy is equal to half mu V0 square, and comparing 1 and 3 we will get the LHS are equal, therefore the RHS must be equal. So L square by 2 mu B square is equal to half mu, it is mu, half mu V0 square, and from this equation we will get L is equal to mu B V0. And what is the expression for U effective? U effective is equal to half mu B square. U effective is L square by 2 mu R square. So substitute mu B V0 for we know that U effective is equal to L square by 2 mu R square. Put the value of L square as mu B V0, so mu 0 square B square V0 square divided by 2 mu R square. This mu, this mu, so you will get half mu V0 square B square by R square. So effective. This is the expression for U effective. So energy is equal to kinetic energy plus U effective. Kinetic energy plus U effective. So total energy is equal to the total energy is equal to kinetic energy plus U effective. And energy is a constant value, and energy is equal to half mu v0 square, which is a constant. Since v0 is constant, this is a constant value. And what about U effective value? U effective is equal to U effective is L square, effective is half mu v0 square b square by r square. Okay, so looking at this picture, this is the energy diagram for the system, and this is the curve for U effective. Here we know that half b square by r square. So this is an exponential curve, half mu v square b square by r square. This is the curve for half mu v0 square b square by r square. And energy is constant. E is equal to half mu v0 square. And what about kinetic energy? Kinetic energy K is equal to E minus U effective, and we know that kinetic energy must be equal to or greater than 0. So E minus U effective must be greater than or equal to 0. So K is never negative, so that the motion is restricted to the region, so that the motion is restricted to the region E minus U effective is greater than or equal to 0. So initially R is very large. So considering our system, initially R is very large. As the particles approach, the kinetic energy decreases. So as the particle approach, this is the difference between energy and U effective. This is the difference between this is the expression for, this is the magnitude of kinetic energy. This is the difference between U effective and energy. So this is the difference. So initially R is very large, the kinetic energy is higher, and when the particles approach or the R decreases, the kinetic energy vanish at a point RT. At this point, the kinetic energy is equal to 0. The kinetic energy decreases when R decreases. When R decreases, the kinetic energy decreases, and at this point, the U effective and energy are equal. Therefore, at this point RT, the kinetic energy vanishes, and the radial velocity is 0. When the kinetic energy is equal to 0, the radial velocity will be equal to 0, and the motion is purely tangential. So the motion will be purely tangential. The radial motion is 0. The radial velocity is equal to 0. So when there is a motion, it is purely tangential, and this is the turning point RT. At the turning point, the kinetic energy is equal to 0, and at a turning point, RT, E is equal to U effective of RT. This at this point u effective of r is equal to u effective of RT, which gives you half mu v0 square is equal to half mu v0 square b square by RT square. Okay, t square, and these two terms are equal, therefore you will get RT is equal to B. Once the turning point is passed, R increases and the particle will separate. In the center of mass concept, the particle mu bounces off the barrier and the barrier of the effective potential. So, in the concept of reduced center of mass, we are considering the two particle problem to a one body problem. So, in the center of mass concept, the particle mu, the particle of mass mu, which is bounces of the barrier, of the effective potential. This is the barrier effective potential, and it is crosses the barrier potential U effective and the bounces of the barrier potential. It is bounces of the it is again moves in this direction, that is R is increasing. So at this point, after this point, R is again increases, so the particle of mass mu is hit at this point and bounces off. So now let us apply the energy diagram to the problems of planetary motion. Okay. Okay, now we are in a position to explain planetary motions using the idea that we studied now. So we are applying the energy systems to the problems of planetary motions here, and we know that the force of interaction of two bodies is minus g m1 m2 by r square. This is the gravitational force between two particles of mass m1 and m2, and obviously r is the distance between them, and this is the attractive potential of the system, which is equal to minus g m1 m2 r. And we know that the effective potential is equal to mu of r plus L square by 2 mu r square, and it is equal to minus g m1 m2 by r plus L square by 2 mu r square. And looking at this expression for U effective potential, and why we are finding the expression for U effective, we have to draw the energy diagram. For that we need effective potential, and looking at this expression, if L is not equal to 0, this term dominate the centrifugal potential. This is known as the centrifugal potential, and the centrifugal potential dominates for small r. For small r, this quantity will be higher, so the centrifugal potential dominates for small r, and at larger r's, the attractive gravitational potential dominates. When r is larger and larger, this quantity will become more higher and higher, because this is a negative quantity. So when we are drawing these two quantities, we will get L square by 2 mu r square is like this. This is the curve corresponding to this equation, and this is 1 by r curve, this is 1 by r square curve, this is minus, and it is minus gm1 m2 r, which will be like this. Okay, so effective potential will be the sum of these two. And let us check the U effective potential and the energy diagram of the system of planets. So in the case of there is a this is the force of interaction or the situation of planets. When two planets are in motion, we can solve the two body problems into one body problem like this. So K is equal to E minus U effective, and K must have positive or zero value. Motion is restricted to the regions K is greater than or equal to 0. So the motion is restricted where K is greater than or equal to 0. K must be positive quantity. So the nature of the motion is determined by the total energy. So what is the nature of the motion? It will determined by the total energy. So we are considering different cases of total energy, and in the first case it is E is greater than 0. So when E is greater than 0, this is the line for E greater than 0. This is the line for E greater than 0, case 1. If E greater than 0 and this point onwards is U effective is greater than E, so the motion is restricted in this area. This motion is restricted in this area. Okay, in this area the motion is restricted in this area, and if the particle is crosses this barrier, at that time K will be negative, so that that is not possible. So the motion is restricted in this area. Okay, so R is bounded for large values, and R is bounded for large values, and the particles can move all this area, and R is bounded for large values but exceed a certain minimum if L is equal to 0. So R must be a certain value, otherwise R must be a certain value, if L is equal to 0, R must be a certain value, and if R is equal to 0, U effective will be equal to infinity. That case is not possible. It will make K a negative one, and that will not be possible. So R must be a minimum value. So the motion is restricted under this area. Okay, so in the second case E is equal to 0. This is similar to the case 1, and here this is the line. This is the line where E is equal to 0. E is equal to 0, the motion is restricted to a small area, and it is like the same as the case 1. In the case 1, the particles can move all over this area. Okay, all over this area. And in the third case it is less than 0. When the value of E is less than 0 and the line corresponding to E less than 0 is this line where A is less than 0. This is a 0 line and this is a less than 0, and here the motion is bounded for both large and smaller. So this line is crosses 2 points of U effective. So the motion is restricted under this area, or it is bounded motion. This is bounded, it cannot crosses this point or this point. So the motion is restricted under this area, or the motion is under restricted to boundaries. The two particles form a bond system. This particle will form a bond system here. And in the fourth case, E is equal to E minimum. E is equal to E minimum. That is, the E minimum value is, this is the E minimum value. The case for E is equal to E minimum, where R is restricted to one value. So here in this point the R is restricted to one point. This is only here we have only one minimum. So R is restricted at this value, or R is restricted at to one value. The particles stay constant distance from one another. So the particle will stay constant distance. They will stay constant distance from one another. If E is E minimum, the particle will stay at least a the particle will stay a constant distance. So this is about planetary motion. This is the curve for E effective, U effective. This is the curve for U effective. This is the sum of these two curves, these two dotted curves. This is a curve for U effective, and we have studied different cases of energy values, and the energy values will gives you the, or which will determine the motion of the particles.